Okay, our first unit is going to be our introduction to the class, introduction to chemistry. You'll notice as I advance through the slides that each of the slides has a number, and that number corresponds to the page number of the guided notes that I have posted on Canvas. So at any point that you want to use those as a reference points for what we're doing, that's just why I included those in the slides. So what is chemistry? Chemistry is the study of matter and energy and how they change. Atoms are connected by chemical bonds. We break those chemical bonds, we form new substances, and we end up with chemical change, entirely new chemical formulas. What is a substance? A pure substance has a uniform chemical composition and can either be classified as an element or a compound. In this particle representation, these particle diagrams are something that I want you to get used to doing and used to looking at. Little circles that in different colors represent different elements. So for instance, nitrogen is diatomic, which means that two atoms are connected together of the same type, but this entire thing is one element. This orange circle is copper. Copper is not diatomic. It only has one atom per unit. But a compound such as water is made up of atoms of different types, and that's what really distinguishes an element and a compound. We'll get into that in greater detail at a later time. An element is a pure substance that is only composed of one type of atom. Like I said, you can have elements that are composed of units of 8 atoms, like sulfur. Ozone is O3, but as long as they're the same type of atom, it's an element. Compound, on the other hand, is composed of atoms of different elements. So we went over water. Oxygen is connected to both hydrogens, atoms of hydrogen, and methane is a compound made up of carbon connected to hydrogen. So I'm going to take a second here to encourage you to pause the video and try to identify in these 3 blocks whether it's an element or a compound. In block A, I would consider this to be a compound because I can see that there's an atom connected to a different type of atom. All of these are the same type of compound, but this box represents a compound. This box B represents an element. I've got atoms of the same type that are connected together, and they're all the same. Box C, I see both. I see compounds and I see elements. And we'll talk more about the reason why this is a mixture at a later point. The scientific method, this should all be, for the most part, reviewed to you. But there's one big reason why we use the scientific method. I like this picture of a snowflake. It really illustrates that nature is built on patterns. And when we talk about the scientific method in class, we use what we can see on a macroscopic or larger level to make predictions about what we can see on a microscopic level. And the reason why the scientific method is so useful to us is because we can make patterns that we can see, and we can apply those patterns to the things that we can't see, that are invisible to us. The steps of the scientific method, you probably have learned that you always have to make sure that you observe first, and then you can start to hypothesize, and then you can begin to experiment, and so on and so forth. But really, these 4 bigger stages of the scientific method can be applied in any order. You can start by testing a theory to see if those observations fit the theory. You can start with a hypothesis, a prediction, and then go straight to your experiment and make more observations. The scientific method is not just a set of steps that need to be carried out in a particular order. But there really are 4 categories to what you would do in an experiment. We're always collecting observations using our 5 senses. And from those observations, we can then make a hypothesis or a prediction. We test it. And then if it stands at the end of the experiment, it can become a theory or a law. And that's a big distinction. A theory and a law are different in one aspect. And I like this analogy because a car has many moving parts. It takes the dual airbags to keep the passengers safe. It takes the antenna to be able to listen to the radio. It takes the drum brakes to be able to stop the car. It takes the front wheel drive to be able to drive through snow. Each one of these things does a very simple action. A theory is essentially a collection of laws. A law is something that's very simple, like the steering wheel. It does one thing. A theory, on the other hand, is a very detailed explanation of why something works. And oftentimes it is composed of other laws. A law is a simple statement or an equation that reliably predicts patterns or events in nature. On the other hand, a theory is a complex explanation that addresses the how or the why of the patterns or events that we see in nature. I pulled up two examples that actually deal with the same topic. The force of a gravitational field is predicted by this mathematical equation. The masses times each other divided by the radius of their distance squared. That's a very simple explanation as to how the gravitational force between two objects works. On the other hand, Einstein's theory of relativity predicts that there is this fabric that everything floats around in called space-time, which is governed by his complicated math equations, and then there's these pictures that show how space-time bends. That would be a theory, because that theory is built on several simpler ideas and facts of nature. A model is a visual, verbal, or mathematical explanation of a phenomenon. Really, it's a representation of a law or a theory. A model is a way for us to take something that we have as a law or a theory and to make it easier for us to understand. Like this picture, I love this picture. This picture is one of the first photos of an individual atom suspended in midair. This is actually a strontium atom suspended in a magnetic field. The question is, well, what does it look like? Sometimes we're going to draw pictures that are simpler to represent something that is very complicated. It's made up of protons, neutrons, and electrons, and everything else that we know that atoms are made up of. You've already worked with models, like last year. Here's our good friend, the cell model, right? The lysosome, the ribosomes, the cilium, the cytoplasm, the mitochondrion. All of these very complicated organelles within an animal cell can be represented by a colorful picture, a model, to make the cell theory more approachable. The greenhouse effects. How is climate change being impacted by solar radiation? Well, this picture makes it very colorful and easy to understand that when the sun's rays come into the atmosphere, gases such as CO2 and H2O and CH4 are very good at redirecting heat back to the surface. And if the concentration of these gases increases, it would stand to reason that that heat would have nowhere else to go. The more CO2 we put into the atmosphere, the more that it heats the atmosphere. That's another model because it illustrates a very complex theory in a very colorful, simple, and visual way. In this class, we're going to be talking about the difference between thinking macroscopically and thinking submicroscopically. Macroscopic, being able to think about things that you can see or touch with your senses. Submicroscopic level thinking, imagining, playing pretend, the ability to think about pictures that are invisible to us. I take salt and I mix it with water. This is what's going on behind the scenes. I'm taking tiny little particles and mixing them together so that the salt looks like it disappears, but really what's going on? The salt particles are just mixing together with the water.